skora, բայց ասում եմ սպանի, բան, արեք հավելարդուրը, ասում եմ դեպի, բան, առաջին բայց մենք դրատեսում։ Դա շուտով դեռ ես ոնց ռոբոտիկս է ուսուցիչ եմ։
Երրորդ անգամ եմ անցել։ Մի հատ բան է արել, պատմեց այդ բանը, շատ անցել, մյուսը ինչ է սպասել շատ։ Չի ֆայլեցի։ Այլի պրոյեկտի արել, ասել, բայց դրամանի դեպի չեմ իշմարել։ Այդ երրորդից կարող եմ ստացվող։ Ինձ դուք ասել եք, որտեղ շարքում երրորդ անգամ եմ բանը լսում եմ, ինձ եմ արել են արել։
Երկրորդ անգամ առաջին բանը
So this is the camera. Let me show you the important functions that we use. As the focus apparently is automatic. White balance and automatic. But brightness and brightness is stable. White balance. Heto zoom zoom out, zoom in. Since we're now it can move. Then you can lock it like this.
With modulation or no?
All right, let's start. Today I don't really have a presentation. I'm mostly going to be going over a few pretty simple concepts, so don't really have to worry too much about presentation. Quick thing before I start, is there any questions from yesterday that anyone would need answered just before? All right, good. So one thing I'm going to go over today, just a quick overview, is I'm going to explain nodes. I did not get to do that yesterday, just in terms of time. I'm also going to be going over the KCL equations, Kirchhoff's voltage equation, and the Kirchhoff's current equations, as well as just going over voltage and current dividers. So that's just a brief overview, so that's what we have in store. And I like the format that it was yesterday, which was roughly 30 minutes of me lecturing and then about 30 so minutes of questions and just going over everything. So I'll kind of try to stick to 30 minutes of just new information and then anything that needs to be cleared up. That sounds good to me. What about you guys?
That sounds good.
Perfect. So. Oh, I'll just yell. So one really important concept is what's called the node. And the node is, it's a little tricky to explain. It is, the best way I can describe it is a... That's fine, I can go. Can you guys hear me all right?
Yeah,
So the node is a region in the circuit itself that is somewhat defined by its position relative to other components. So in this simple circuit consisting of 3 resistors, right now their values don't matter. This is a node. Why? Because in the path of current, when current is flowing through this initial wire, it hits this resistor. This resistor will have a voltage difference between it, and then it'll be this node. This node will all have the same voltage across it. This section of the wire here, this section of the wire here, and this section of the wire here will all have the same voltage potentials. These 3 regions will, this node is the ground node. That's a concept I'll get into right after. But these are the 3 major nodes, and what separates them is the fact that these distinct areas have different voltage potentials. You can have nodes with the same voltage potential. Let's say, hypothetically speaking, this resistor had 0 resistance. So then these 2 nodes, so physically there's a resistor here that has 0 ohms. It doesn't make sense, this was a wire. But these 2 would have the same voltage potential, but they are still separate nodes. So that's something important to know, is that generally speaking, they have, I would define it as areas of the circuit with different voltage potentials, but at the same time, they can have the same. For the people just coming in, I was just explaining the concept of the node, in which it's just areas of voltage potential within the circuit. I quickly talked about the ground node. The ground node is basically with any given circuit. I'll just draw a really quick one right here. I briefly explained the concept of the ground yesterday, right? Right? Or no? Did I talk about the ground yesterday? Basically, ground is an area of a circuit in which it is connected to a large body of electrons. So the Earth is, if you look at the back of your house, at least in American homes, I'm not sure about Armenian homes, quite honestly. In the back of your home, you'll probably have a giant wire just sticking right into the dirt. And that's for your electrical outlets. It's because the Earth is full of electrons. And so for the flow of electricity, everything will basically flow to the ground in a sense. It's kind of weird to draw like this because hypothetically speaking, you're going through this loop, but at the same time, you're not going completely through the loop, you're going down into this. It's the actual real concept is a little different from our theoretical diagrams, but it's just something you have to deal with, sadly. So yeah, a ground node is an area in which you're connected to the ground. The ground node voltage is always defined at 0 voltage. So in this small circuit here, I have 2 nodes. With this, I should use different colors, but yeah. This is the first node, this is the second node. This one's going to be 0, the same as this one. Why? Because it's the ground node. Something briefly to go over. Oh yeah. A quick thing, just in case I didn't say it already. For a resistor, when resistors experience voltages, it is experiencing a voltage difference between it. So, and this kind of segues well into the voltage divider, current divider. So, I touched on this briefly with just some quick number examples yesterday. And also, do people get the node, or did I just mess up my explanations? Is that good?
Yeah.
Okay, perfect. So when it comes to, I'm going to be talking about the divider equation, so voltage divider and the current divider. So in a voltage divider, usually you're looking at resistors in series or components in series in a lot of cases, especially when you're talking about AC circuits. It gets a little weird when you're talking about in parallel because, let's do this. Let me just draw a parallel. In that, these two resistors in parallel will actually experience the same voltage. So when you are simplifying a circuit, it's better to just kind of just make this circuit a little simple. Get the equivalent resistance of these two. Let's say it's 2 ohms. And you guys know from yesterday that this would be 1 ohm because of the relation between resistors in parallel. These two are going to experience the same voltage, even if this is 4 ohms. These two are always going to experience the same voltage. And if this is 5 volts, it doesn't mean that these are going to experience 5 volts. It just means they're going to experience the same divided voltage from this. So, does that make sense? Okay. So with the voltage divider equation, it is basically a mathematical way to show how much voltage is experienced across each component. So let's say that this is still a 5-volt battery. This is the 1 ohm resistor right here, and this is a 4 ohm resistor here. If I wanted to find the voltage across this resistor here, I would just do, the initial voltage on the battery, times the resistor I'm looking at, so let's call this R1 and this R2, R1 over R1 plus R2. It's a really easy equation. And that applies for this one. The only difference to find the voltage across this would just be Vn times R2 over R1 plus R2. So yeah, it's called the voltage divider equation because proportionally it goes out, it just works pretty well. And if you extrapolate to a more complicated circuit, it really is the fact that the higher the resistor, the higher the resistor value generally, the more voltage is going to experience across it. And it's just proportions. It really is just proportions. Let me erase this. So you guys got that? Any immediate questions about that?
If it was R3, would you say plus R3 at the denominator?
Yes, yeah. In this case, you don't do that because you put these in the equivalent resistances. So let me just make this 2 just so mathematically it translates. But yeah, if it was a slightly more complicated circuit of R1, R2, R3, it would be the same situation of, if you want to find R2, it's Vn times R2 over R1 plus R2 plus R3, and so on and so forth. And so you could do something similar with the current divider equation. It's slightly different because you're not looking at the current across the resistors themselves or components. I'll just say components from now on. You're actually looking at the current going into and out of. Because, just a quick aside, if you look at a resistor right here, the current, I'm about to take a huge leap of faith in my memory because I just may be wrong about this conceptually. If I have a current I going through here, I1 going through here, it's going to be the same I1 going down here. That sounds right. Yeah, okay. And so, yeah, that is right. And so if I have a slightly complicated circuit of, and so that basically means that when I have this circuit right here, all of these resistors will I1, I2, and I3 all equal the same I. They're all the same current because it's going in third series. The voltage divider equation is most useful when you're looking at components, resistors, and parallel with one another. So if I have this example right here, so in this equation, you see I have let's say I have a big I as my initial current going through it. There are two things I know off the bat. One is that these branches are not going to be experiencing the same current going through them. Well, if they were all 1 resistor ohms, they'd actually all be the same current going through them. And let's say this is 1 ohm, 2 ohm, 3 ohm. And the other thing I know is that at the end, the same amount of current is going to end the circuit basically. Down there. So the I going out is going to be the same as the I going back in. The difference is that this I1, I2, I3 are all going to sum to I. So just 2 equals I3. So this is where the current divider equation comes in, and it's a little weird in that current wants to follow the path of the least resistance. So it makes sense that the most current we're going to get is out of this branch because it has the least resistivity. I'm sorry. And it's like current is similar to water in that it will follow the least difficult path. And so it's a weird situation where the math makes sense. It's just a little wonky. In that you can't have the same equation. I'm purposely going to write the wrong equation, so please don't memorize this equation or write it down. It's not going to be the situation of the current that I1 equals I in times R1 over R1 plus R2 plus R2. That's not how this works because that would insinuate that you get the least amount of current out of this branch and the most amount of current out of this branch, which is completely the opposite. When in reality, the current experienced I1 through this branch is I1 times the sum of the other resistors. I should have done this with 2 branches because I'd be a lot more confident about my math right there. But yeah, it's the basic concept of you look at the other resistors than the one you are in series. And when you get to bigger circuits that have resistors in series and parallel and all that, basically you're just going to abstract it out to the simplest possible circuit. Typically, if you only have, in these most complex simple problems, when you have only a battery or a voltage source or a current source and only resistors, you can abstract everything out to be 1 resistor and then go from backwards and just figure everything out through that with proportions. So yeah. Does that make sense to everyone?
Is there a ground node in this circuit?
Yeah, this is the ground node here. You don't have to write in, well, no, I'm not going to say that. The ground node is important. Sorry, was you asking about a ground or a ground node?
Ground node.
Oh yeah. This entire portion right here is the ground node. Because this is all 1 node, because all of this region right here is going to be all going to be 0 volts. These have a shared voltage in this area. This node right here is going to have a completely different voltage. But it is good to note that these resistors themselves are going to be experiencing the same voltage across them because they're resistors in parallel with the battery. Does that make sense?
Yeah.
Okay. Any questions about that immediately? Do you have questions?
Yes. Is the voltage of ground is equals to 0 or not? Or formal value?
Sorry, can you repeat that?
I said, is the value of ground voltage is equal to 0?
Is it always 0?
No.
So, sorry, can you repeat it?
I think we can have a formal value for ground in any circuits.
Oh yeah, you can have a formal value for it. It's 0 relative to the circuit. It is the 0 value relative. Does that answer your question?
Yes.
All right. So for the sake of everything, just make it 0 volts. That's how I was taught, and that's probably how I'll continue doing it for a while. But it is 0 relative to everything within the circuit. All right. Okay. And so now I'm going to be talking a little bit about KCL and KVL. Those are Kirchhoff's voltage and current laws. I don't have to go too much into them, I guess, for the... All right. So you kind of saw me do this. Actually, no, I won't go over this. That's actually something really easy to explain verbally. No, it's not. So in this example, if I have a current going, okay. So, yeah, that makes sense. So if I have a current going out like this, and the general flow is going to look something like this, and my main current is going to go through this, it's going to split at these two nodes, and this is going to be the same, and it's going to combine back into the original at that. And so I then know that if this is, let's call this I1 and I2, I then know that big I equals the sum I1 and I2. And, okay, what else can I do with that? Okay. And so basically you can apply this to more complex circuits. If I have this little thing right here, because then these two would get separate voltages. So different currents, honestly. These would have the same voltage across them. They have different currents across them, depending on the value of the resistor. So let's call this I3 and I4. I then know that I1 equals the sum of I3 and I4. That's a very simplistic way of explaining Kirchhoff's current law. But it is the general idea that in the ideal circuit, you're not losing parts or numbers or any electricity. So when you're doing nodal analysis or any sort of circuit analysis, you never have to really worry about it. If you add everything up, there's a good chance you got it right if you started with the same value at the end. Because of the fact that, let's simplify this circuit here for the sake of example. And that this circuit simplifies out to, from here, I can do this. All right. These are the same circuits. The only difference is if this is R1, R2. Actually, let me give these values. This is 1 ohm, this is 1 ohm, this is 1 ohm, this is 1 ohm, 2 ohms, 2 ohms. This is going to be 1 ohm, this is going to be 2 ohms, this is going to be 1 ohm, this is going to be 1 ohm. Does everyone understand how I got that? Or do I need to go over that? Okay, perfect. And so then I can combine these two into 1, and so I get 2. And then these are in parallel, so I then have this into 1. And then I have the equivalent thing as V2. And so from there, you can figure out what the current is going through if I know that this is, let's make it an easy one of 4 volts. I then know, and this is 2, I can then find the current. And then I can work backwards, desimplifying my circuit and breaking it up back into the component parts. And then from there, find the currents, and then so on and so forth. Does that make sense? Mm-hmm. All right. How am I doing on time? Around 20. Okay. So let's talk about the voltage version of this one really quickly. So let's say I have this right here. That's the same circuit actually. So 1, 2. So going back to what we were talking about with nodes, let's say this is 5 volt. It is basically the idea. Also, something to note about KCL with current is that if I'm looking at this node right here, if technically speaking, the sum of all currents going in and out of that node in any given node is 0. What that means is that if I have this node, and let's call it E for the sake of argumentation, and I have I1 going in, I have I2, and I3 going out, and this is something of just personal preference of, you can define, okay, so when I do it numerically, I define currents going in as negatives and currents going out as positive. It's completely arbitrary. You can do it the opposite way. I suggest you pick one way to do it and just stick with that because it's just easier to do that than switching constantly. If you know conceptually, you'll never make the mistake, quite honestly, but it's just better to stick with one, in my opinion. You just know fundamentally that if in is negative, or 1, and out is positive, or 2. That's true for any of the nodes. I know that in this node right here, and this is, let's say this is, well, it's going to be the same. Well, that was a terrible example. No, wait. No, I'm good. That doesn't matter. But yeah, it's that same concept. Any questions with that exactly? Alright, so, okay. What can I do with this part? KVL. Okay. And then, extending it a bit more to the KVL side of, KVL, the voltage law side. And I'll just use a quick example to try to help explain it. This node right here is going to be 5 volts. I know it's going to be 5 volts because that's the immediate voltage experienced at that node. I know that if I look at this value, and quick note, remember that our main constituent relationship is V equals IR. And so, if we know that the voltage experienced across a resistor is the difference between the 2 nodes, did I mention that or did I not?
I think you did.
I did, okay, good. So if the current, the voltage across a resistor is the difference between the 2 nodes it's sitting between, we know that the voltage experienced across this resistor here, V1, is going to be 5 volts minus E, in that E is our voltage at that node. All right, and then from there, you can kind of, this is still the current one, honestly. To me, there is a difference between KVL and KCL. I can't think of any immediate good examples of KVL. I will get that to you tomorrow at the beginning, because I can't think of any good examples of KVL at the top of my head. Basically, I'm going to go with KCL still, actually. This is still KCL, the example.
Sorry, if you could just write a little bit bigger.
Oh, I'm sorry.
Thank you.
So, V1 equals... No, I'm thinking, is this big enough? Okay, good.
That's good.
Okay. So, V1 equals, so that. And I can then find that the voltage across the current experiencing that, I1 equals that over R1. And through that, you can kind of see where I'm going in this, and that you can apply this to every I1, I2, I3, and that'll be 0. So then you can find E, the voltage at that node. Does that make sense what I'm saying, or do you guys want me to write that out? All right, I'll just keep it going. And so that's kind of all I had prepared today in terms of the actual lecture, just giving a brief overview of nodes, KCL, KVL, and did I teach anything else? All right. Do you guys have any immediate questions about this material or any general questions about tangentially related topics?
Yeah, can we use the analogy of pipes with the KCL possibly? Like if we have a pipe that is branching out into 3 or 4 different pipes, then the water that goes out of the main pipe, the amount of water, is equal to the sum of the amounts in the 4 pipes, like in terms of current.
Yeah, that's exactly what it is. Yeah. In his example, it is a main pipe feeding into 4 smaller pipes, right?
Yeah, and for example, another small pipe coming into the big pipe with negative sign, we could take that.
Yes, I think yes. You can have a negatively sized pipe, but I know what you mean. Yeah.
Yeah,
Yeah, that makes sense.
in that case, what analogy can we use for the voltage law? Or
The voltage. All right. That's why I want to explain the voltage law tomorrow, because I need more things for the voltage. The voltage law is very similar in that the voltage law kind of just states a similar concept of voltages themselves do not disappear. That's all it. KCL proves at its base level, at least from my interpretation of it, is that current does not disappear. And KVL does the same thing. It just dictates that the voltage does not disappear. Like, you guys know physics. You guys know the concept of matter can either be destroyed or created. It's the same situation, just in an ideal circuit. Obviously, you're going to have power dissipation. You're going to have all that. In an ideal circuit, especially when it comes to diagrams, you're not going to lose the voltage. You're not going to lose the current. That's what these laws are explaining. But at the beginning of tomorrow's lesson, I will go over KVL, because that is something I need properly prepared for. All right. Anything else immediate? There's nothing immediate. I can go into digital logic. Do you guys want to do that? All right, let's do digital logic. Digital logic is honestly one of my favorite topics. It's really fun. So this is more so what I was going to on Thursday, but it's fun. So do you guys know the difference between analog versus digital in the case of voltages? All right. So an analog voltage is a voltage that is continuous. It ranges from, in this example, it can range from 1 to 100, meaning I can have voltages of 1 volt, 2 volt, 3 volt, 1.87 volt, 99.8 volts. The difference is that we're talking about digital voltages, is that I can have, well, in the case of digital voltages that we use in our computers, you can have 2 voltages, high and low. So typically, that translates to a 0 for a low and a 1. A 0 for a low and a 1 for a high. And I guess a quick question is, if I want, and this is a question I want you guys to think about and answer very briefly, is that if I want a system in that I have a low voltage and a high voltage, how would I differentiate those? Any ideas?
Can you repeat your question, please?
If I have a system in which I have, if I want to use digital voltages, if I want to have a digital system, how would I differentiate between a low voltage and a high voltage? Any ideas so far?
Like this?
Well, what does that mean? Any ideas?
Resistors. We can just use resistors for that.
No, I'm just talking about you want to have a system in place that you are differentiating between high and low. This is not a technical question. Well, it is a technical question, but you're not building a circuit in this very simple question I'm asking. It is what differentiates a high from a low voltage? What would the cutoff be? How would you determine that cutoff?
don't we need to use transistors? But I don't have an idea how that goes.
The question is separate from it.
That threshold voltage, maybe.
Yes, that is yeah. So you need a threshold voltage. In that, if we have a range of voltages, because in the real world we have analog systems on the outside. For example, my speaking volume is analog. I go from very quiet to very loud, and that applies to everything. In that, when we in the real world have an analog system, we have to translate it into a digital system for any and all computers. For example, your microphone, when you're at a computer, you're on a Zoom call or whatever, your voice is an analog system, but your computer has to digitize it. It has to do that through various means. And the way that we differentiate between the high and the low values is through the threshold. And so if we set an arbitrary threshold at 50, this is low, this is high, and 50, 0, 100. And this is a good starting point for digital logic. The only problem is that we have what's called electrical noise. And that is when an electrical signal is sent, in the ideal world, there is no electrical noise. There is no problem. Electricity flows perfectly and nothing happens. In the real world, we have disruptions. We have what's called electrical noise. And these are just disturbances that occur from everyday life, quite honestly, the background of the world, that causes the voltages to kind of sputter out a little bit. And the way I say this is that, let's say I have an analog voltage of about, I chose very bad numbers because 45 volts should not be in your computer to my knowledge. Let's say I have an analog voltage of 49.9 volts. Is that a high or a low?
Low.
Exactly. But if I have some noise, and let's say my noise is equivalent to 2 volts, I'm now in a positive voltage noise. Now, I have 51.9 volts. And so my low signal is now going to be interpreted as a high signal. So I need a new system in place to counteract that. And the way you do that, initially, well, can anyone think of any immediate solutions to this problem?
I can think of a softer solution with,
What?
like,
I can't really explain.
You can draw if you want. All right. Well, the next step would be to have 2 different thresholds. One for this is as high as the low as I'm going to get, and this is as low as the high I'm going to get. So that would look like this. In which if I have 0, 100 here, and my cutoff for what is considered low is anything less than, let's say, 25. And anything greater than a 75 is a high. And so, does anyone see anything immediately wrong with this system?
The middle part?
It's hard to differentiate between values from 25 to 75 when they're higher.
Both of those are true, in that you kind of miss out on this middle part. And I'll get more to this on Thursday because I need major examples to explain why this part is, it's a problem, but it's not that big of a problem, quite honestly. But yeah, it's the same problem as when you have a low X high. You have a problem if you have a 24.1 or a 76.2, and you have a negative, noise doesn't really get that bad unless, if you have negative 7 volts of noise, you're in a not good place. So let's say you have negative 2 volts of noise and positive 2 volts of noise. Obviously, you're going to get into the X range. And so you need what's called static discipline. Static discipline is weird, and I don't like it. It is basically the concept, and this is going to be very awkward for me to explain because I failed my exam with this. It's not awkward that I failed, it's obvious I don't know it. I do know it, it's just weird for me. In that, okay. This is 0, this is 100. And the concept is that I want my output voltages, whether it be an input, I want my, oh God, I hate this so much. So the basic concept is that an output voltage and an input voltage are different values. That's the baseline concept behind it. It is that I want my out. Okay, can everyone think how this system would work as I think about it, so you have a general idea in mind? The basic concept is that different voltages mean different things, if that makes sense. In that, if I have if I have an output, if I have a high output, okay, I'm going to straight up just look this up. Sorry, one second. I'm not going to waste your time with me just thinking about that. I need to look this up. Any questions as I look this up, so I'm not wasting your time? All right. All right. So the basic concept is that you want your, so these are going to be the highs, these are going to be the lows. You have something going that way, something not like that. An input, output will be I'm going to save this for Thursday entirely. Static discipline, in my opinion, is one of the hardest parts about digital abstraction, and it just confuses me because it is a lot of differentiating voltages. The basic concept is that, and I'm not going to get into specifics, I will get into specifics on Thursday, is that you just want different thresholds for different types of values. So you want the voltage threshold for an output that is a low to be different from an output that is high, from an input that is low. Sorry.
Oh, and lastly, we will be having a Fusion Friday where I'll talk about Fusion, I promise. It'll be great. Okay, so today we're going to tell you about nuclear mass and stability. This is going to overlap, at least at first, with a lot of basic chemistry ideas you probably have learned, like chemical reactions. If you think about nuclear science as a whole, it's pretty much chemistry, but you can change elements. So if you've gone through thermodynamics a lot, I was telling this story earlier today, they hold all of the equations to the expectation that you don't switch elements. And this is just doing equations where you're like, oh crap, you might accidentally change elements. Ooh, modern metallurgy, not metallurgy, what is? Alchemy, modern alchemy, okay. So first we're going to go through a bunch of the notations and some of the really basic concepts, and then we're going to do example problems so you can work through it, and we're going to show you the online databases where you get all of the information needed for solving a nuclear reaction. So, we're gonna, A is the atomic mass. It's always on the top of your element, and then Z is your atomic number. The mass is the number of nucleons as a whole. Z is the number of protons, and then Q, lowercase, is the charge. So it's going to be a positive or a negative number, and then it's not necessarily 1, it can be more, it can be less. It's going to be basically your difference electrons to protons. Haha. And this equation can be simplified by writing it in a lot less materials, a lot less numbers. And basically what it's telling you is, if you take, first off, all mass is conserved, right? So everything that goes into our equation also has to come out of it. And we have boron, and if we add a neutron to it, this total number on the bottom is going to stay the same. 5 plus 0 is 5, 3 plus 2, still 5. Then on the top, we have 10 plus 1, 11, 7 plus 4, still 11. our boron is going to turn into lithium and helium because we added a neutron. We'll get more into why this happens. It has to do with the energy that it outputs and the split being the two most favorable elements that come out. But because neutron is the form of radiation we give it, and alpha is the form of radiation that comes out, because helium is equal to an alpha. Well, it's equal to an alpha for our purposes. And so alpha is the form that comes out. We input boron and we get lithium because these are our main elements and these are our radiation formats. We always make sure to include the isotope that we're using, which is the type of the element based on the neutrons involved. And I'm also going to write this equation down just so you can see it when we switch slides, because Brendan's going to go through a real-life example problem, as promised, that has to do with cancer radiation that involves this reaction. Okay, any questions so far? Awesome. All right, well.
BNCT, a treatment performed to selectively destroy cancer cells injected with boron compound, is done with a minute amount of neutrons that are irradiated to cause a nuclear reaction in the boron-injected cancer cells. First, protons are accelerated to the energy level of 30 megaelectron volts and to about 25% of the speed of light by the cyclotron, which is a circular accelerator dedicated to cancer treatment. The accelerated proton beam is transported to the neutron irradiation treatment section. Then the transported proton beam is irradiated onto the beryllium target to produce neutrons. Neutrons are decelerated until the energy is lowered to an appropriate level for treatment and are irradiated on the cancer-affected area. A patient who will undergo the therapy is given the boron compound intravenously in advance. Cancer cells selectively uptake the boron compound. Irradiating a neutron beam to those cancer-affected areas will cause a nuclear reaction with the boron. The nuclear reaction generates energy to destroy a single cell. Boron injected in this way results in the cancer cells being selectively destroyed. Different from other radiation therapies, BNCT will destroy only cancer cells without damaging any normal cells in the vicinity.
Yeah, so the same way we talked about yesterday, how there's X-ray therapy, proton therapy, there's also neutron therapy. There's a bunch of different kinds of radiation, and all of them are used for different cancer treatments. But now we're going to kind of go through why this is set up the way it is, and kind of explaining all those parts that they kind of brushed over throughout the video. So, a lot of the things they kind of said were really random. So, they talk about a cyclotron, using that accelerator to get protons up to speed of about 30 megaelectron volts. These treatments can be done with nuclear reactors or with accelerators, but in general, it's a lot easier to build an accelerator than it is to have a whole nuclear reactor just next to your hospital. So a lot of these things are designed using those accelerators because they're just easier to work with. But then, why 30 megaelectron volts specifically? So we're going to take a look at one of the many, many databases that if you're a nuclear scientist, you will constantly be checking.
Janus, ooh. You guys, if you do nuclear, you're going to be on Janus so often.
So this is Janus. It's organized by a very large, by the Nuclear Energy Agency, and it's basically a large database of how different particles interact with different elements. It can be a little bit of an unruly website, mainly because, Zoe, can you move? I can't see. Mainly because there's a bunch of different databases. Back during the Cold War, no one wanted to share their data with each other, so there's just kind of a bunch of separate databases that people have been maintaining since about like the 50s, 60s, 70s. But once you kind of start to understand this website, it becomes very easy to navigate. So we're looking at for neutron therapy, but they talked about shooting protons into beryllium. So let's check the incident proton data.
Okay.
And then we like to use ENDF because it's the American one, and we're going to use the most up-to-date one. And then we can just go to the cross-sections. And the cross-section is basically a measure of the probability of something interacting with something. It's related to the area, but it doesn't always directly correlate to the size of the atom itself, because particles can kind of do whatever they want when they're at that small of a scale and interacting with these different kinds of energies. So we want to go to beryllium. And we're going to go to beryllium 9, it's the only naturally occurring beryllium. We're going to look at the cross-section for literally anything happening. One below it. So there's kind of just a lot going on in this graph, but they talked about 30 megaelectron volts, and we're going to look at why by going into a zoomed in portion of the graph here. So we're going to look at the area of about 1 to, let's say, 50 megaelectron volts. So 30 is right about in this region, which is this nice region over here that's flat. And it's also in the area of about 500 millibars. It's about as high as you're going to get for this kind of thing. The higher cross-section you have, the more likely to interact, and you want everything to interact. Otherwise, you're just shooting protons doing nothing. But there's this area to the left of here that has much higher cross-sections, but we're not going to use that. Mainly because when you're trying to do a medical procedure like this flat region here gives you a lot more leeway for, your protons aren't always going to be exactly 30 mega-electron volts. Maybe a little bit higher, a little bit lower, but you want to know exactly how much you should be expecting, and kind of having this flat cross-section allows you to really easily predict that. If you have this kind of jagged mountainous area, your procedures might go very differently every single time, and that's not really something that you want. So for now, we're going to minimize that. Okay, but then protons can interact with a lot of things. We can make neutrons out of a lot of different things. Zoe has written up on the board.
What wrong?
Zoe, you wrote?
I did it backwards.
Yeah.
Yeah, you're right. So
we can make neutrons out of a lot of things. What we're trying to get here is neutrons, but why beryllium specifically? The other material that we make neutrons out of a lot, and especially what we use in fusion reactors, is lithium. They both make neutrons. They both pretty easily to access. The big major difference is, has anyone ever handled like pure lithium metal? Has anyone ever actually interacted with it? Can you tell me anything about lithium metal?
Super reactive.
Yeah. Basically, if it touches water, it will set on fire.
Yep.
And there's a lot of water in the world. You really don't want things to be setting on fire or exploding while you're doing this. Beryllium is super stable. They use it to build components in rocket ships. It's really easy to work with, and so it's much better to have just sitting around as opposed to lithium. And it gets us our neutrons, which is really what we're there for. Then we're putting the boron in the cancer cells. But then how are we actually getting the boron into cancer cells? So, as we said yesterday, cancer is it's cells that are growing, and they're growing a bunch. So basically, you can just put it in some sugar, attach it to a sugar molecule, and knowing that your cancer cells are going to be dividing a lot more than your non-healthy cells, especially because brain cells especially don't really grow past the age of 5, you can know that the boron will be getting only into the cancerous cells. But then, why do we care that boron's into cancer cells at all? So, boron loves neutrons. It loves it so much. It's the same, boron 10 specifically, is what we use in our nuclear reactors as well to control reactions. If you put boron 10 in, one of the biggest ways, like the safety features in a nuclear reactor, is you just throw a bunch of boric acid into the reactor, and it will absorb as many neutrons as it wants, and it's a great way to just kind of shut down the reaction. Boron, then, if we look at the carry tables, which is this thing here, another database maintained by a Korean university. Boron then, when it absorbs a neutron, releases an alpha. So an alpha, again, as we mentioned yesterday, is a kind of radiation that goes very short distances. So basically, that boron in that cell will split, it'll create a high energy alpha. That alpha will do its damage right there in the cancer cell, and it won't damage the nearby cells. So that's really the big benefits that we have. So you want to take it from here?
Yeah, so the Curie table of nuclides. This is a really great representation of all the different isotopes that we know and all of the basic information in each of them. And then each individual isotope is going to act a little bit differently. And so so here's a zoomed in version. We have like a bunch of the same element, each of the isotopes. You click on the one that you want the information for, and it's going to give you this basic information. Okay, here we go. So we have the atomic mass, and it's to a pretty exact decimal point. It's in atomic mass units. And you guys know that that's, roughly the atomic amount of protons and the amount of neutrons, yeah? Okay, and then we have the excess mass and the binding energy. These are very related. The higher the binding energy is, the more energy you would have to place into this to get a reaction. It's also going to tell you if your element naturally tends to be more prone to fission or fusion. So if it's more prone to fission, it's more radioactive. That means it's splitting off right there. And then your excess mass is going to be, the more negative it is, the higher your binding energy. And that basically refers to the differential in atomic mass, since that number is not wholly accurate. And you'll find when you do your full calculations, unless you include the excess mass, you're going to end up just a little bit off all the time. So this is an offset to prevent that. And then some other fun information you can see. We have our percent abundance. So we're looking at sulfur 32. If you multiply all your information for sulfur 32 by 0.9502, and then you go through each different isotope until you get to 100, you can come up with natural sulfur and all of your information for that. We have spin values. It's a stable isotope. And then it tells you some of the most common parent nucleides. So these are reactions that would produce your specific isotope that you're looking at. If you were to do an example problem, you would come to this page for each isotope that is in the equation. Like, to solve this, if I wanted to find the energy outputted or inputted in any case, I would just, come to Curie table of nucleides. Sorry, this feels like housekeeping, but I promise you'll use it later if you do this.
I've spent so many hours just staring at this website.
But wait, I have a question.
Yes.
Regarding the same reaction that you've written here. Oh, okay. Regarding the same reaction that you've written here, is it not possible to instead calculate, say, Gibbs free energy for both outputs of the reaction in order to get how much energy output or input we have?
So yes, it's very possible, because E equals mc squared.
Yeah.
Everything is related.
Sure.
It's just more simple to use the values on here because it includes the excess mass. So if you use Gibbs free energy, you're going to be off by like that exact amount.
By exactly the excess mass.
Yes,
okay.
for each of them. So the excess mass for these two.
Okay. So basically, what you're saying is the say, I don't know, polished up equation would be Gibbs free energy plus 4 of these excess masses for each of the things we have. So for beryllium and boron. So that we're not off, basically.
You almost. So yeah, you would need to convert them all to the same units, but once you're in the same unit, that's exactly right.
Okay, great, thank you.
This is pretty much, how many of you guys have seen this before? No? Yes? Some of you? Okay. This is pretty much have you guys seen this before minus the radiation? Okay, so it's the exact same concept. It's completely the exact same concept. We just add a couple variables to confuse you, because it's how nuclear science do be. Okay, next slide, please. Oh, so these are, I guess I kind of actually covered this. Here's an equation for the binding energy. This is exactly what you were just talking about. It has the conversion E mc squared, fun, some Einstein in there. Your atomic mass units directly convertible into mega electron volts. And then we have our basic amounts for 1 AMU, neutrons, protons, electrons. This is all information that you'll accidentally end up memorizing. Okay. Oh, examples. Next slide, please.
You want to talk about where AUA is defined from?
Do you want to talk about it?
So I guess one thing I want to comment on is like excess mass and like the nature of like what like the standard like neutron weighs all comes from carbon-12. So through like if you've ever seen E/mc squared, anytime that you bind these things together, they all take some of their mass and convert it to energy. We kind of treat mass and energy as the same in nuclear, just because they're constantly being converted between each other. They use that mass get turned to energy, and that is what allows them to bind. So that means that the more things you shove together, the lighter they'll be, technically. But the way that it's defined is from carbon-12, so the most common isotope of carbon. We just kind of take whatever that weighs divided by 12, and we're like, that's what a standard thing weighs. So anything that is below carbon will actually have positive excess mass, because it's lighter than carbon. It has more. It will have on average more than one atomic mass unit per atomic mass, whereas heavier things will almost generally be negative.
Okay, so we're going to do some examples. Do the board notes. Okay. Dun, dun, dun. All right, well, this is going to require us to go to the theory table. I have some notes written down, but they're on my laptop, so give me like half a second. Sorry about that, not the most professional. Here we go. Can you pull up the theory table for them? Thank you.
You sharing this all 32 then?
Yes. Are you sure? You had them pulled up right before this. Okay, I'm logging in. Do you guys have Canvas here?
What's that?
Oh, it's like this terrible app they use at MIT and a bunch of American universities to grade.
Oh, we have Moodle.
It's like the exact equivalent of that. So I'm going through the login process. It's in here. Pulling it open.
MIT has changed which website it uses like every year and a half, so this is like our third or fourth one that they've had us use.
Oh, we wish we'd changed.
And we always wish we changed, and somehow it gets worse.
Yeah.
More notes. Okay. Could not find it. That is okay. I guess we don't even have to calculate it because we're just pulling it through. I think this was, I am very sorry. I should have had you guys do this independently, but I don't know how to get you the website. But we magically pulled our binding energy from here. Small fluke. So you guys, it's to make us more personable, right? If we did everything perfectly, then we wouldn't be relatable. Okay. We're going to skip this slide because I think it's redundant.
Wouldn't it just be though, like 31 times 931 that you said?
Yeah, that's why I feel like
okay,
this is plain.
Yeah,
Okay, so we don't need to do this 3 times, but you would get your practice with the database. I just decided to be kind. And we're going to take like one more external look, and we're looking at a capital Q this time, which is the energy overall. So we have lowercase q, that's going to be our charge, and capital Q is the energy or the heat that we're looking at in the equation. This can be either positive or negative, which will tell you if it's on either side of the equation. And then lastly, mass is conserved. And this last third, this ending part of the slide reinforces your point that it's all the same. You can get here a variety of ways. There are just easier ways. There are slightly more complicated ones, but all is all. Beautiful. Okay, now for binding energy, which we did look at briefly last time. This curve, if you'll remember, told us about fission and fusion, and over here we have fission, which is very reliable, but also a very slow incline. And over here we have fusion, which is a lot less reliable, but the energy potential is huge. And these are all experimentally obtained, and they're basically just telling you, again, the binding energies, the energy potentials from each of these reactions. There's a theoretical way to find all of these. It's called the semi-empirical mass formula, and we'll take you through it step by step and just identify some of the main components of it. I think I have one more. Two more. Okay. So this shows the difference between the experimental and the theoretical data. It gets, the higher, the heavier your elements get, the more reliable it is. At the very beginning, it's all over the place. This information is luckily really, really known. Oh wait, no. Yeah, so this information, we have some experimental points, and that's kind of what we go off of. Yeah, there's something called the island of stability, which I'm going to touch on next. And it's a huge unknown in the nuclear field, and that's because if you think of the way that neutrons interact, and protons and electrons, it's all very similarly. So do you guys remember learning about valence shells in electrons and how that makes it more and less stable and less likely? Okay. Exact same thing happens with neutrons. So based on that, we get these almost irregular seeming, very, very stable isotopes. And our first few numbers are known: 28, 50, 82, 126. These are tried and true, very stable. They're called magic numbers. There's going to be another one. We know there has to be another one. Nobody knows where it is. People have been trying, people have been synthesizing. It's a mystery. We had an assignment our freshman year where we had to discover the island of stability, the next magic number. It took hours and hours. No one did it successfully because then we probably would have gotten a Nobel Prize. Stressful. Okay. Yeah, now Brendan's going to walk you guys through the actual formula that would mathematically predict it, which, fun fact, lines up very, very nicely with this. We're not in the chaotic region yet.
Yeah, so we have this mass formula because it's really nice to have formulas for things as opposed to having to check a database for every single nuclei whenever you want to look it up. It's much better to just have a formula that you can kind of plug some things into and get numbers out. But the way that this is structured with binding energy is in a series of terms. So this first term is the volume term. It's a constant times the number of nucleons that you have, the mass of the thing. And this directly correlates to the volume of your nucleon. So basically, every time you add another little ball into your collection of balls, if you guys learned about the strong force as within nuclei, thing that holds them all together, every time you add a new thing, it's one more thing that they're all interacting with. And so as you get bigger and bigger and bigger, your binding energy is going to go up because they're just interacting and being attracted to each other. But then we have to make some corrections. So first we have the surface term. So this accounts for the fact that on the surface of whatever sphere you're made, all those ones on the outside aren't going to be interacting with as many things. They're only touching one side. On the outside, there's just nothingness. And so in the first term, we saw that it's A, but now we have A to the 2/3. And this directly goes with the fact that if you think about the number of things, your volume is related to your radius cubed, right? Your lovely volume of a sphere formula. But for your surface is r squared. So you get 2/3 of that total number of nucleons. And for both of these, there's just a constant that adjusts it so that the curve is as close to the real data as possible. Then we move on to make another correction. So in your nucleus, you have protons and neutrons. Neutrons, they're all just kind of there, they don't really care. The protons, though, they're all positively charged. And as you've all probably learned in intro physics, positively charged things repel each other. So you have to account for the fact that every proton that exists has a charge of 1, and it's pushing away all the other things with a charge of 1. And then, as you also probably learned in physics, the Coulombic force is directly related to 1 over r. So that's where we get that magic little total number of nucleons to the 1/3 on the bottom. And then we have the final thing, so our symmetry term, our symmetric term, which is just a measure of how many neutrons you have compared to how many protons you have. And again, as you learn with valence shells, as you fill them up, things like to be together. For the nucleus, there's actually 2 shells at the same time. There's the neutrons fill the energy shells, and then there's a separate filling of the neutrons and proton energy shells. And when there's way more neutrons than protons, the atom isn't really happy. They want to be about equal, because otherwise you have 2 very different energy shells filled, and everything kind of wants to be in the lowest possible energy arrangement. So as your difference in neutrons and protons increases, you're going to have less binding energy. Then here we actually see what these terms are, and most of these are just a measure of making sure the formula gets closer. But you can also think of it as kind of which term dominates. And as you go on, kind of seeing how that formula, as we saw in the graphs, and so we talked about, change over time, bigger atoms have different terms dominate. So, A grows with time, but so do Z and N. So it's that trend and where we get that stable. So at the very end of the spectrum where it's all kind of wonky and the formula isn't quite accurate, it's because one little change changes a lot. Versus when you have 100 something, one little change is a lot easier to adjust to. But then we also have this delta term. So that's the even, odd, even, odd. So again, just how electrons like to pair, they like to one spins up and one spins down. Protons and neutrons like to do the same thing. So if you even things, it's more stable because every proton has a friend, every neutron has a friend. If you have an odd number of both, so you have 7 protons and 3 neutrons, that doesn't exist, but I just kind of chose random numbers. 1 proton and 1 neutron are both left without a friend, so they really don't like to exist in that configuration. And if you have, an odd number of protons and an even number of neutrons, or vice versa, it's kind of neutral, so we don't really add something or we don't subtract anything from the binding energy. And so then, taking this binding energy curve, binding energy is very closely related to stability. You can kind of see for each different atom, for each element, what the stability trends are, how many of them exist. And as Zoe mentioned with the magic numbers, right at that 50 we see a big spike. There's 10 stable things with 50 protons, but outside of that the numbers quickly drop and fluctuate. And as you can see again, we're tracking the even numbers and the odd numbers separately. They show trends that are very comparable to each other. If you're looking at just the ones with even things, they all behave roughly the same, and just the odd things, but when you compare even and odd, they don't quite work that well together. When you look at the larger range of all the elements, you get the random magic number spikes, but overall it's, again, a pretty flat trend. And then when you look at very specific things, you can see that there's a lot more elements that have an even total mass as opposed to an odd total mass. Because with odd, something has to be left alone unpaired. But you can also see that as you go into heavier and heavier elements, things at the bottom of the periodic table, you get a lot more neutrons than protons. And you can kind of think of this in the form of, with more and more positive protons showing up, you need more neutrons there to kind of keep them apart. If you have any even numbers, that Coulombic force would just kind of tear the atom apart, so you need more neutrons to really hold the nucleus together. And this also really plays into how radiation plays out and why it kind of exists as a thing. For every atom, if you start throwing in extra neutrons, extra protons, it wants to go to a stable form, and so it'll decay through radiation to its most stable form. And you can kind of see for each mass, for every total mass, it's a balance between how many neutrons you have and how many protons you have. And if you have too many neutrons, you're going to shed neutrons in certain ways. If you have too many protons, you're going to shed them in a different way. And the most common form of this is positron and beta decay. So positron is you're spinning out a negative electron, or positron is spinning out a positive electron, and you're consuming protons, whereas beta decay, you're spinning out an electron, and you're creating protons from neutrons to try and find that nice middle point at the bottom of your mass parabola. And again, with the magic numbers, the actual nuclear shell model itself.
Yeah, this is what I was mentioning before, the neutron equivalent to the valence shells and electrons.
It's got a lot of the same names as stuff that you see with valence shells, so 1p, 1s, and all that. But where these magic numbers actually come from is where there's big gaps between the energy levels. So if there's a big gap in energy level, then the things there are really hard to excite. They don't really want to change. They're perfect where they are. And so that's where you get those magic numbers. And so this is why we know that there must be another magic number out there somewhere, but we don't know where these gaps are going to be. We kind of just have to keep experimenting until we find that gap.
So this is back again to the question of an island of stability. I actually already talked about this, but the graphs doubly illustrate. You can kind of see each of them marked out on different points, and they fall closer to the end of the scale than the top, and then it just tops out. We don't know what happens. Maybe if any of you are looking for a nice little nuclear Nobel Prize in physics, could be worth looking into. We can also plot this with dependence of alpha decay and half-lives, because that is very related, at least on this scale, to the physical size of each of the elements. And then the way that people are trying to solve this is they synthesize really, really heavy elements. And you do this with accelerators. This is where you hear about CERN. That's the appeal. You see how large, how super heavy can you make these, and you basically get stuff that can exist on the order of, I don't know, nanoseconds. It's honestly less than a nanosecond, and it exists very, very briefly. And the goal is to observe it as quickly as possible and then be able to break it down so you can maybe, hopefully, get some very relevant information from it, but it's difficult.
Sometimes science is elegant, and sometimes your plan is just slam stuff together until it works.
Yep.
We know that well.
Exactly.
We spend a lot of money, so hopefully it will work.
And here's a chain isotope. More here for the beauty of it than relevance, because we talked about it again. But does anyone have any questions about today's lecture? I know it's a lot less sexy than nuclear technologies, but this is definitely the building blocks of like everything that follows will take, you know, this basic style of interaction into account. And then we can start talking about the specific types of radiation, how they affect you, more into fusion. Ooh. What time is it? How much? Oh, okay. So we've got like a nice 10 minutes. Maybe 20 if people want to stick around, but you definitely don't have to, for questions and answers. Cool. Yeah?
For the liquid drop mass formula, the even, my question goes. Okay, so for the even, odd, even, and odd. So my question is like, what is even and what is odd in this case?
So even and odd are referring to the number of protons and neutrons. So each one is said once or twice. Because you're looking at the number of neutrons and the number of protons. So it doesn't always matter what your total mass is. What you're worried about is, do you have an even number of protons and do you have an even number of neutrons? Or do you have an odd number of protons and an even number of neutrons? Stuff like that. Because, again, as I said, if we look at the nuclear shell models, so like, if you have protons, they'll fill one of these, and essentially to the left or right of this, you'll have neutrons filling their own form of this. So you're looking at whether the protons are paired together and whether the neutrons are paired together or not.
If you want to further the analogy between electrons, you could almost think of it as spin. Like electron spin, but not with electrons anymore. Yes?
Yeah, my question is a bit weird, I think. It's on curing the cancer, the video that you showed, with the help of protons. I would like to know, is it possible to teach our organism to cure cancer without actually radiating it? I mean, the same way that COVID vaccines are created, the mRNA vaccines, like they teach the organism without actually infecting it. Now, can we teach our organism to cure cancer without actually radiating it?
So, like, I hope. We're nuclear engineers. We think of this a lot through the nuclear lens. I'm sure there's a biologist out there working on it, but that's not really our field of expertise.
Yeah, I think that one bit of food for thought is that COVID is a virus, whereas cancer is your cells just uncontrollably replicating.
I just heard that from a YouTube interview.
Huh?
That, it is possible to the same way that they teach our organism to fight COVID, they can teach as well to fight cancer. But I thought, what if they can replicate the same actions that, like the way you showed boron therapy does, like they can replicate those actions for cells, and without actually being radiated, those cells can cure themselves.
Maybe? I have no idea, but that's very fascinating.
Yeah, with all cancer treatments, the goal is to damage the cancer without damaging anything else, and radiation is just one way to do that, but people are exploring a billion different ways to try and cure cancer. I think cancer will probably be that question that sticks around forever.
Thank you.
Oh. Thank you.
So, this question is probably going to be very, towards either one of you. Since I was not yesterday, I don't know which one it is. Who is into fusion? Not fission. Great, my question is here. Right, so, I'm pretty sure you've seen some videos or stories about making homemade fusion reactors small for high school projects or whatever, with deuterium and basically a metal net with very high voltages and a vacuum. So my question is this: if we have a sustainable, say, deuterium fusion reaction, in a very small vacuum chamber, and we have a window and we're measuring some alpha radiation coming off, so we know that deuterium is becoming into basically, helium. So we're having helium alpha particles. My question is, if we shut it off, it's going to shut off. And what's the point in fusion that we want to reach right now, as people, as humanity? What's that point of fusion? Is it the point of having self-sustained fusion reactions we can harness energy from, or what's the idea there?
Okay, so self-sustaining fusion is in some ways a goal, but I think that logically you always have to have a way to shut it off. Fusion always has to be shut off a goal. So I don't think we're ever going to reach a point where we try and create just an unsupervised star. However, there's something called an R value, and that represents how much energy can be taken out versus it takes to put in. And these tiny ones have just minuscule, 0.0000001 R values. And if we want something to be viable for commercial use, we need to reach about 2. Right now, the highest R values are just barely above 1. And then, honestly, if we want to look at something that can get put on an energy grid and something that can theoretically power maybe an entire continent or a fourth of a continent, we're looking at on the value of 10. And it's definitely possible, but it's, I don't know, I don't want to say fusion's 30 years away, because I think it's closer than that. I think it's about 5 years away. But I think that our values of 10 are maybe 30 years away at least.
Okay.
From an outside perspective, listening to professors and the fusion people talk, it does seem like fusion has made it to the point where the field is dividing a little bit. So there's ITER being built right now in Europe, a massive fusion reactor. MIT is building is designing a separate device right now.
It's called Spark.
Oh.
Yeah. So the fact that we're getting to a point where the field itself is dividing and taking 2 separate routes of how we best achieve this, I think is a good sign for there's a lot more in the technology developing, and we're going to see where we get there from here.
It's the good competition.
Yes, and the big technology that pushed this is high temperature superconductors, because they let us get crazy magnetic fields around 20 Tesla for confinement, and this is just something that you couldn't feasibly have large enough plasmas, you couldn't control them without something powerful enough. And high temperature superconductors hit the market, I want to say 30 years ago. And they started getting used for fusion around 10 years ago. So it's a quick uptake. They're very fascinating. They're also where I do all my research. So I can answer questions about these maybe on Fusion Friday.
So the dangers of fission is pretty apparent, and people already know most things about fission, but my question is, what are the exact dangers of fusion? Because I haven't really read up anything about it.
We can talk about trading inventories.
Do you want to tell them your pessimism on
No. That's Amelia's black box. That's not mine.
Okay, so from my perspective, the biggest danger about fusion, because we're not going too far into the self-sustaining realm, it's turn-offable. We have confinement, but also they're never going to build a reactor without the safe confinement. It's either it happens or it doesn't. So the most dangerous thing about fusion right now is that when it's done and over, even though it doesn't output any radioactive waste, all of the materials that were used, the physical Alcator CMOD, the physical Stellarator, well, it's going to be a tokamak, which is a shape we'll tell you about later. Again, sorry for the jargon. But the actual metal itself is going to be radioactive waste, and you're going to have to dispose of that in a clumsier way than you would from fission, because it's much larger in very specific shapes. But honestly, if you ask me, I think that's not terrible. It could be worse. You'd likely have to ground it down and put it inside of a casket, but this is a lot more power with a lot less waste. I need to stop thumbing up, you guys. I'm sorry.
Yeah, there definitely is a degree of we are stopping ourselves from going off on tangents because we could probably talk forever about a billion things. Our group chat argues a lot.
Thank you guys. Woo. Oh wow, what year are you? I think that's a we could plan one for sure, and maybe we could just take one day of Wednesday. Although, ooh, I would be very interested.
That person there,
cool, but I think there's
she's actually, she went to school, I believe, with our professor in Georgia.
Do you guys want to see my
She works on fluid force. There are resources. She knows way more than she does. She just every once in a
I have, but I
we were told something similar about your human observatory. Like,
So it's not been working.
yeah, like you used to do a bunch of stuff and then kind of just they stopped repairing it.
Yeah, you can go there now, but you go there because this is how it used to use it, and even the people last night. So
Oh, the observatory.
Oh, it's on my like, insanely long list of things I want to do.
Yeah, that'll be the main combination of
Huh?
This one is official.
Let's get everyone excited with the tech and then start the building blocks. Get into all the
At least in our experience, it's more about classes at MIT is a professor will tell you a bunch of math, and then you're like, why do I care?
You like zoom out and then we try and zoom in, but we will get there. I don't think we can give you any certificates of the course, but when you apply to MIT, there's a section where there's like extracurriculars and programs you participated in, and you can say that you participated in MIT, like MISTI, I can write that down. Yeah, okay.
Or you can structure it in one of your essays.
Yeah, you can mention it casually, it'll work, but this is a pretty
Thank you. Have a good day.
You're like, yeah, I think I have
I just like that whole message. When I got one course, well, like I just like I was that way, and then the course was then they applied to a bunch of other colleges.
Yes. Thank you for coming. What's the I kind of. I've only had one today and yesterday. Just the three.
Yeah, the real hero running around with my
Thank you so much. Yeah. I'm Zoe.
There's Bethany.
I think Zach might have gone home.
You went home?
He might have, probably. I think. No, mostly he was like, I don't want to sit here for 2 hours, so I think he's gonna like, I think he like might walk around a bit.
Okay, that sounds like a fun time. So, yeah, you guys feel like I'm just going to show you around after work a bit, to walk around in the city, because I may leave before 5.
Go take care of your toddler. Go take care of your toddler. He's not focusing on us.
How was it?
It was good. I had a whole slide that I threw out the window because I got like halfway through trying to find the notes that we had on it and realized I actually was going to be so useless anyways.
This is great experience.
Absolutely.
Each one. I didn't participate like in presentations. I'm just a volunteer, but it's really interesting the part that
Today was kind of clunky because there's a lot of, we're trying to get them, you know, the building blocks and the notations and whatever, and that's never going to be as fascinating as, beta decay.
There's also, everything is simple when you thought about it for 3 years, and now you're like, how do I think about it from ground zero?
Yeah. Teaching is hard.
Yes.
I cannot imagine being like a secondary teacher trying to teach multiplication. Like, I feel like I'd go insane.
I feel like you multiply the number, what do you mean?
Like, it just happens.
Yeah. Oh my god. Yeah. Nice to meet you.
Okay, you're doing a great job with the camera. It stopped working.
It wasn't working during ours.
The comments are turned off now, right?
Did you guys see the comments yesterday?
I haven't. I heard about
Who was it that was told that we were, was it us or was it Zach that was told that you're wrong?
No, Zach was wrong. We just got a bunch of brownie faces. And Bethany got a bunch of 420s.
Why?
That's what happens when you have memes in the comment section.
Yeah. I didn't.
Arik was also there, like yelling at the camera person who didn't exist. He was like, zoom in!
He was texting us.
Zoom in!
He was texting his members directions to whisper to the camera guy.
I was with the camera.
Oh my goodness.
Yes, I did. I have zero experience. So, I just learned
Power pose?
Power pose.
I was also talking. So,
Today we're going to talk about celestial mechanics and like orbits and stuff. Oh boy, I got a laser pointer. So, as I believe I mentioned yesterday, planetary orbits aren't circular. They're all elliptical, although to different degrees. So, and this can be said for basically everything that orbits the sun. So here in the diagram, we got the orbits of the terrestrial planets and their eccentricities, which I'll talk about in a sec. So Venus is actually the closest to being a circle, and Mercury is furthest of the 8 planets. It's kind of a shape there. And then over here, we've got the orbits of a couple of comets, though the Halley's Comet doesn't come around very often. So it's a very big orbit, so it's going all the way out here. Anyway, so they're all elliptical, and there are many elements of an ellipse. So there is the major axis across the wide way, and the semi-major axis is half of that. Then the minor axis and semi-minor axis. Then the foci, or it's the plural focus, and we have 2 of them in each place. And then the distance from the focus at some point r can be expressed by the semi-major axis times 1 minus the eccentricity squared over 1 minus the eccentricity times cosine of theta. And eccentricity describes how far it is from being a circle. So, and that can be expressed as square root of 1 minus the semi-minor axis squared over the semi-major axis squared. So, there's several laws that Kepler thought up back when people were thinking of astronomical rules, and there's 3 of them that we think about. There's Kepler's first law, is that all planets move around the sun in an elliptical orbit, as I already said, and the sun is one of the focuses. pretty simple. And if an orbit is circular, which it can be for not things that aren't orbiting around the sun, then the foci are at the same point. And then Kepler's second law, there is that a radius vector joining any planet to the sun sweeps out in equal areas in equal lengths of time. This happens because angular momentum is conserved. So basically, that means in orbit, things travel faster when they're closer to the thing that they're orbiting, and then slower out there. So, as you can see in the diagram, if something was orbiting for 1 month, it would sweep out that much, and then go slower, and then for about 1 month, it would go that much. But these two areas are the same. And when things are orbiting the sun, when it's closest, that's called perihelion, and when it's farthest, it's called aphelion. And then Kepler's third law is that the square of a planet's period is proportional to the cube of the semi-major axis of its orbit. And then the actual equation, it can be expressed like this, with 2 pi over that, and then the g, which is Newton's gravitational constant, it has this value, but I'm not doing math today, so whatever. And then n is the solar mass, or if you're applying this to something that is not orbiting the sun, it would just be the mass of whatever the object is orbiting. So with satellites orbiting Earth, a satellite orbiting farther from the Earth will take, So a satellite orbiting Earth would take longer to orbit. If it's farther from Earth, it would take longer to orbit, have more distance in its orbit, and its average speed would be lower than a satellite orbiting closer to Earth. So Newton used the work of Kepler and others to establish his laws of motion, and they help explain why satellites stay in orbit. And we'll go over each law and how they apply to orbits, but first we have the law of universal gravitation. Force equals gravitational constant times the mass of each thing in the two-body problem over the radius squared. And in the case of Earth and its satellites, the mass of Earth is a lot more than the mass of the satellites. So we can basically neglect mass 2, and it doesn't really relate to how much force there is. It's completely determined by the mass of the Earth. And this is true for the mass of the sun and relative to the planets as well. So the first one is the law of inertia. We all know it. And so that things in motion tend to stay in motion unless acted on by an outside force. So the motion that it would want to do without any force is just off into space. But the force applying it pulls it towards Earth, so it goes in an orbit. And that's why they don't fall to Earth, because inertia keeps them from doing that. The second law basically allows us to do calculations for the orbit. As we can see here, if we interpret that with acceleration in a circular motion being velocity squared over r, and solving for it, we can get that, which lets us determine how fast it needs to be going to stay in a circular orbit. And then the third law explains basically how we launch rockets, and exhaust shoots out one side, it goes the other way. It's not really that complicated. But then the velocities let us know how to keep it in a certain kind of orbit. Because if it's not fast enough, it'll just fall back to Earth. If it's at one perfect one, it'll be a circular orbit. More than that, it'll elliptical. And then if you get fast enough, it'll get to escape velocity. And escape velocity for the Earth is about 11.2 kilometers a second. And also, this is why astronauts on the ISS experience weightlessness, because satellites are technically just always in free fall. Now, a little aside for binary stars, there's lots of kinds of stars, and it's been estimated that about half of stars in the Milky Way are binary stars, and they can be broadly sorted into 3 categories: visible binaries, where you can see that they're actually separate stars; spectroscopic binaries, where we can tell that's 2 different stars because of the red and blue shifting when they're moving away and towards us because the wavelengths are getting compressed or contracted slightly because of the movement. And then the eclipsing binaries, where we can tell that they are 2 because the intensity varies over time depending on if the dimmer one is in front of the brighter one, it has a lot less. If the brighter one's in front of the dimmer one, it's just a little bit less. And if they're not eclipsing each other, it's like a baseline. And we'll talk more about stars tomorrow and back to mechanics. So obviously things can orbit each other and not be dominated by a much heavier thing, so like binary stars. So in this case, we have 2 radii of one of the other, and then a larger one. So if we take the gravity force and centripetal force in this equation, and then substitute the reduced mass, which is used a lot in 2-body systems, we can get this orbit equation. And if we use the third law, which can be expressed as such, rearrange it for V and substitute it into this equation, we can get this. Rearrange it for T, we can get this. And then if we use convenient astronomical units of AUs, the value of G, and solar masses, and put period in years, we can calculate the period of the binary system with this. Now, in circular orbits, A is just the radius, and it's the semi-major axis in elliptical orbits. So that's really a lot of the basics of orbital mechanics. It's not really past just like normal circular mechanics. And a couple things from yesterday about like dwarf planets and how dwarf planets don't clear the orbit of the things around them. So for Pluto, it has a satellite, Charon, in which it forms a binary system, and that's why it's a dwarf planet, because it's affected by the orbit of Charon. And then also someone asked about Voyager 1 when I was discussing the Oort cloud, and it's currently outside the orbit of Pluto, but it's not going to get to the inner edge of the Oort cloud for another like 300 years. So that was very fast.
Does it mean that, for example, Earth's orbit is does it mean that, for example, the Earth orbit is not affected by the moon?
So one of the other students said yesterday that they thought that's like it's possible that Earth technically might be dwarf planet because it might be slightly affected, but I think, hang on, let me look up the exact ratio, because...
What was the question?
Yeah, is Earth affected by the moon's orbit? And like, it is to a certain extent, as everything is with universal gravitation, but the mass of Earth...
So it means that it is, I mean, we can just... It's not important for the calculations. Does it mean that?
Yeah, so the mass of Earth is 2 orders of magnitude more than the mass of the moon, where the mass of the Earth is about 6 times 10 to the 24 kilograms, and the mass of the moon is 7 times 10 to the 22nd kilograms. So it's essentially negligible with universal gravitation, though. And then the mass of Pluto and Charon, I believe Charon's about half the mass of Pluto, and that's why it's affected.
Yeah.
I have a question. I heard that in general, in general astrology, there have been a consensus that some of the gas giants can be considered like unlit stars, or are considered in some ways bases for a star. Do you think if things went different, we would have probably had a second star from one of the gas giants?
So one thing with stars is that, that I'll talk about more yesterday, is that how stars work is that basically they're so massive that the pressure that they create in their cores causes fusion just naturally, which is what we're trying to recreate with fusion on Earth. But, so, I guess an unlit star is essentially just a ball of gas. So I suppose you could define gas as like planets that are just made of gas as unlit stars, but yeah, the essential difference is that stars are massive enough to create fusion in their cores, and therefore give off energy and light and all that other stuff. But that has to be much greater. I believe there can be planets that, there are planets out in like the universe that orbit around binary star systems, and I don't know much past that about that, but yeah, that's the principal difference between gas giants and stars, is that stars are large enough to create fusion and therefore like energy and stuff.
Nobody has any questions? I was late. Can you say some things that you said before, like in beginning?
Yeah, so planetary orbits are circular, they ellipses, and so is the orbit of basically everything that orbits the sun, and there's Venus is the closest to being a circle, and Mercury is the farthest to being a circle of the 8 planets. And there's also things like comets that orbit the sun that are very much not circular. And there's the elements of the ellipse, the major axis, the minor axis, and then the semi and major and minor axes, and just half of those. There's the focuses at each end. The distance from the focus can be expressed with this equation, and then the eccentricity is a descriptor of how much it is not a circle, essentially, which can be expressed as square root of 1 minus the semi-minor axis over the semi-major axis, also square root. And then, did we get to Kepler's first law?
So I'm going to ask a question. The shape of of the orbit is like out, does it mean that the speed of the planets or any object is not constant?
Yes. So that's in Kepler's second law, where basically when it's orbiting closer, it's going to be going a lot faster and then it's going to slow down. So the amount that it sweeps, the area that it sweeps is equal, but because it's a lot farther out, the radius of that is a lot larger and that compensates for the fact that it's going slower.
The sun was in the focus, right?
Yes, the sun is the focus of, is in one of the focuses of all of the orbits. Yeah.
My question is more in regards to the orbits themselves. So if, like, for example, we take the orbits of Mercury or the planets that are really close to the sun, so can we say that in practical theory, those planets are free falling into the sun, like sooner or later?
So the whole free-falling thing has to do with the first law, where any stable orbit, they're always going to have the inertia that keeps them from falling into what they're orbiting. Because if they weren't in a stable orbit, they probably would have already fallen in at this point. Though with the, since stars in their life cycle, they like eventually start like, they grow over their life cycle. So eventually, like, the mass of the sun will change, become bigger, and it will, that will upset the balance. But then there's also the fact that the sun will also expand to just consume the inner planets. So eventually the stable orbit will be upset, but that's not going to happen for quite some time. The sun's pretty young right now.
What was the third law?
Yeah, Kepler's third law is this relation here, that the square of the period of the orbit is proportional to the semi-major axis of it, the cube of the semi-major axis of its orbit, and then the actual equation that the proportionality comes from is this 2 pi under the period, and then the gravitational constant, and then the mass of, in this case, the sun with the planets, but if it's like a satellite orbiting Earth, it's going to be the mass of the Earth. Yeah. And that's also used for like calculations and things.
What was alpha again? The A.
Oh, A is the semi-major axis of the ellipse, which is, so the major axis is the entirety of the way across, and that's just like the longer radius. The universal gravitation, that's fairly all there. And then, yeah, in the case of like Earth, where one m is much larger than the other m, the smaller m is negligible, and force is completely determined by the mass of the larger object.
R is the radius?
No, the distance.
Yes, R is the radius of the orbit, so it's the distance between the thing that is being orbited and the object orbiting. So we're going over inertia, how inertia keeps it from falling into what it's orbiting. The force equation just allows us to determine, gives us the derivation that allows us to determine the velocity that it needs to not either, for its orbit to not decay or escape, or at least stay circular. And the third law is basically, well, the third law is like how we get it up, like rockets just launched with exhaust. But then there's also like decays of orbits where if it has an initial velocity, if it's too small, it will decay and fall back to Earth. If it's at one particular, it will go circular. It's larger but not escape velocity, and it will be an elliptical orbit, and if it's escape velocity, it will just not orbit at all.
How fast it came forward determines the type of orbit, right?
Yes. However fast the velocity is tangent to the Earth. Up just makes it go farther away from Earth. So obviously, you need enough force to get it off the ground, but that's not the orbital part.
So there's been a lot of conversation in like the general scientific community about the James Webb Telescope. I kind of wanted to, I mean, of course, it's a very deep, more technical question, but could you, like, in layman's terms, say what really makes it special, like compared to the other telescopes that we have floating around in the orbit?
Yeah, so I actually haven't been following what the James Webb Telescope is, but I can certainly like. Much, so it looks like the James Webb Telescope is just doing like a lot of different things. Like the headers. I think it was built to do like a lot of different space exploration things, and like find determine like what chemicals are in the air of like other planets. And things like that.
All right.
Question, like you can go. There's
Can I ask an off-topic question?
Yeah.
So how does it feel to study it?
It's fun. It's not easy. There's an expression used a lot of the time, like drinking out of a fire hose, where there's just so much to do and so many things, and it's very intense. But it's ultimately quite rewarding. I actually study nuclear science, like the previous two presenters. I just took a couple classes my freshman year on astronomy, and I liked it in high school, so ultimately I liked nuclear science more.
So, you kind of mentioned fusion, like fusion reactors and stuff that we're trying to develop. So with fusion reactors, what do you think nowadays is like the biggest obstacle that we have to having it be completely usable as an energy source?
Yeah, so there's lots of things with fusion, with currently we put more energy into making the fusion than actually getting out. So yeah, I'm not a specialist in fusion. I took like one class on it, and I'm leaning more towards fission specialty. But
yeah.
I'm sure Zoe will be talking plenty about it on Friday.
Makes sense. Could you talk a bit more about the data like that MIT? What was it that like surprised you the most? What were your
I can't honestly say I was surprised by the difficulty of the classes. One thing I enjoy a lot is being like around people who are basically just doing the same thing as me and like have their own extremely narrow interests in science. And I suppose that could be said for a lot of engineering programs in a lot of places, but yeah. I think a lot of people say that the best thing at MIT is the people.
So, what do you think? You are a nuclear scientist, yes? What do you think in the future maybe nuclear science can bring for the medicine some profits in the future, in medicine particularly? What do you think?
I don't really do nuclear medicine, so I'm not, like, I know its basic applications, especially the ones that Zoe and Brendan have already gone over, but I haven't really studied it past what they've basically already gone over, where it, like, to be used for cancer treatment, and like how protons can be used because of their range. Yeah.
Like related to X-rays, for example. So new ways can be created or investigated. I don't know.
Yeah, I mean, like, nuclear medicine is definitely an important part of, like, the nuclear science community. I just know very little about, like, the bio things.
Okay.
What are your thoughts about Armenia so far?
Very nice. It's been pretty foggy the entire time I've been here, so I'd like to see what I can see on like a sunny day with like views, but I like it so far.
It's nice to hear.
Can we, particularly me, I graduated from Yerevan State Medical University, so can I take some courses related to nuclear medicine or in America or in Canada? It is provided in USA, for example.
Yeah, there definitely are classes about nuclear medicine. I can check right now what classes there are available at MIT. So I looked at our course catalog. I don't actually think we have classes that focus on nuclear medicine, but I'm pretty sure we do have research groups that do it.
Research particularly. And can I be involved in some programs, for example, in researches as a doctor, for example?
Like
I think which requirement do you think they will have?
I do not know about the world of postdoc things. I'm currently a junior, so.
Okay. I understood. Thank you.
To your profession, if I understood you're a nuclear engineer, I would ask, like, in current developments in nuclear engineering, what would you say? Are reactors nowadays much safer than, like, during their first inceptions? And, like, would you say that the fear against them would sooner or later be subsided?
Reactors are absolutely safer now than they were like back during like the Cold War, and especially because of like, to be fair, a lot of the accidents were caused by extremely preventable human error and ignoring safety protocols. But yes, they are even safer now, and hopefully eventually the fear about nuclear reactors just spontaneously blowing up will subside, but part of being a nuclear engineer is like trying to give it a better rep, a better rep, in, like just in general public and stuff.
I also heard that, like, in general, in recent years there have been slight problems in constructing some reactors, because the people in that field have been slowly dying or fading away, and because of that, some of the materials are construction things were not available. What would you say about that problem?
I honestly don't know anything about like the actual any about knowledge being lost with people. I know that particularly in the U.S. because we haven't been building reactors, we've gotten less good at doing it efficiently, and therefore it's more expensive for us to build them than say Korea building their Gen 4 reactors. Yeah.
One more question in regards to the old generations with reactors. What do people mean generation 1 to 9 or what? How many generations of them there are and why are they? What classifies a change in generation?
So I believe we're currently on the 4th generation of reactors, but I haven't actually taken the fission reactor class yet. I've taken the fundamentals of it, and I've taken neutron science, but a lot of the generations are sort of based off of design conventions for periods of years. Generation 2 reactors are the class of commercial reactors built until the 1990s. Generation 1 would be before that, the very first ones, and then after the 90s we got so Generation 1 reactors are early prototypes. Generation 2 is the ones that I believe they're the ones that were actually deployed for commercial power. Generation 3? Yeah, so it's the technologies associated with them, they're their lifetime. So I found a presentation from someone else. Basically, characteristics of Generation 2, they were evolutionarily connected with Gen 1. They had an emphasis on safety and use of passive safety elements. Generation 3 had a standardized design of all the reactor types with licensing and minimization of investment costs and construction time. They have a higher load factor and a longer life. They have more safety mechanisms with reduced failure probability and with core melting, and they have resistance to serious damage and a higher burnup of which reduces the amount needed for nuclear fuel and therefore reduces the amount of spent fuel that we have to deal with. And some of them can use recycled fuel. Yeah, and in general, they're simplified from Gen 2. They're cheaper. They have more effective fuel use. And then, Gen 4 are currently in development, and I don't think any have been deployed yet. And they'd just be advancements to that, so more safety, better fuel use, stuff like that. So that's what sort of separates them.
Are you lecturing the Intro to Nuclear Reactors course?
Next, reactors? Brendan is taking the lead on that since he's had a year more of classes and has actually taken the fission reactor class. But I will be helping because I do know like the neutronics stuff. Thank you for coming.
Yes, yes,
That sounds. I cannot do that, so it's.
I cannot do what?
You saw me try that.
No. I don't actually understand honestly, but I will I can do it. No, I would like to, but
Yeah, no, I
Where are we speaking?
I'm from Houston, Texas. Have you heard of it?
Yes. I will spend this summer in Ohio, I think. It's working summer.
That's pretty good. Like Saturday, I probably went to do you have a message or something?
Maybe I guess. Which social platform is more?
I just have Facebook.
Okay.
Good. I will.
I can find it.
You're not here for so presumably I'll open the G1 do it 2 times. You know, to get that good or something.
Okay. Okay.
Thank you so much. Thanks so much for helping out. I'll talk to you later.
Bye. Genetic. Won't answer person.
Mikrofon ancak dedi.
Ha, mikrofonu ancak
Hmm.